According to these specs, the armor plating for Hull 3 should be here.
It's delayed again, sir. We can't launch her without it.
My measurements confirm the gauge is off by a millimeter here.
That's unacceptable for the aircraft specifications. We have to remelt these ingots.
This penetration here confirms their objective.
The armor will reach the coast by tomorrow evening.
This section of the North Carolina is vulnerable. What's the tolerance there?
Barely within limits, sir. We need to reinforce this sector immediately.
January 1941. The Boston harbor is gray and biting cold. Steam rises from shipyard smokestacks, curling into the winter sky. Workers move with purpose along icy docks, their breath visible in short, sharp clouds. Hammers strike steel sparsely, a metallic rhythm punctuating the cold morning. Around them, partially constructed battleships loom, hulks of iron and wood waiting for armor that isn't there. Steel is scarce. Shipbuilders glance at empty yards where thick plates should lie, waiting for delivery that will not come. The Navy's most advanced vessels, meant to defend the Pacific, sit vulnerable, their sides exposed. Every day brings tension. The Japanese fleet grows bolder, and America's ships must be ready, even as resources lag behind strategy. Amid this scarcity, another metal hums quietly in warehouses: aluminum. Lighter, strong, and abundant from domestic sources is not traditional armor. But necessity is a relentless teacher. In a world racing toward global conflict, innovation is not optional. It is survival. The question hangs in the air. Can aluminum, once used for soda cans and aircraft frames, shield America's greatest ships? By 1941, the world was on fire. Europe had already descended into chaos. Germany's blitzkrieg over France and the Low Countries had stunned military analysts, demonstrating the speed, coordination, and lethality of mechanized warfare. Across the Atlantic, the United States remained officially neutral, yet the government was preparing for an inevitable conflict. The Navy faced a glaring problem. Its fleet, though formidable on paper, relied heavily on steel armor that was in critically short supply. Steel production in America was constrained by both global demand and domestic limitations. The nation's mills were already committed to supplying railroads, bridges, and existing industrial contracts. International embargoes on scrap and raw materials further tightened supply. Meanwhile, Japan had expanded aggressively into China and Southeast Asia, seizing steel and iron resources for its war machine. Washington understood that a confrontation in the Pacific was likely. Soon, America's battleships might face torpedoes, shells, and kamikaze attacks without the armor they were designed to carry. Naval planners recognized the vulnerability. Battleships like the USS North Carolina and USS Washington were designed with heavy armor belts, capable of absorbing shells from 16-inch guns. But those plates could not arrive fast enough. The traditional supply chain, rolling steel, transporting it, then cutting and welding it into armor, was too slow. The Navy faced a choice: delay ship completion or seek alternatives. Enter aluminum, a metal that had long been considered a strategic asset. Alcoa, the aluminum company of America, was already producing thousands of tons annually, mostly for civilian purposes and aircraft construction. Aircraft aluminum was lightweight, strong, and corrosion-resistant, qualities engineers prized, but had never been used extensively in naval armor. The material's strength-to-weight ratio offered an unexpected advantage. Ships could retain speed and maneuverability even with lighter protective plates. Yet, aluminum could not simply replace steel without testing. Engineers needed to understand its ballistic resistance, its behavior under explosive stress, and its long-term durability at sea. The United States government moved cautiously at first. A series of memos from the Navy Department in early 1941 outlined experimental programs. Alternative alloys should be explored, one document read, with particular attention to aluminum alloys, which may provide adequate protection where steel cannot be supplied in time. Aluminum's domestic availability made it politically attractive. Unlike steel, which relied on scarce or imports in heavily booked mills, aluminum could be produced rapidly at domestic facilities. For the first time, the idea of substituting one of the Navy's primary defensive materials was seriously considered. Shipyards along the East Coast became testing grounds. In Norfolk, Boston, and Philadelphia, engineers examined how aluminum plates could be welded onto hulls without compromising structural integrity. Thickness, layering, and alloy composition were all under scrutiny. Every decision carried immense risk. Too thin, and shells could pierce the hull. Too thick, and the ship's stability and speed would suffer. It was a delicate balance between protection and performance, a balance that had never been attempted on such a scale. By mid-1941, the urgency had grown. Japan's attack on Pearl Harbor was still months away, but intelligence reports painted an increasingly threatening picture of the Pacific. The Navy needed every advantage, every innovation, to ensure its ships could survive the first salvo of battle. Aluminum armor was no longer theoretical. It was a potential lifeline. At Alcoa's factories in Pennsylvania and New York, engineers worked around the clock. Production lines that had once focused on aircraft components now churned out plates for the fleet, each cut, tempered, and tested under exacting standards. The human dimension of this effort cannot be understated. Shipbuilders, engineers, and factory workers labored under relentless pressure. Winter drafts blew across open decks in Boston, and molten aluminum sparkled in the furnaces, bright against the gray sky. Each plate represented not only an engineering challenge, but the lives of sailors who might one day rely on it. The urgency, the stress, and the stakes combined to create an industrial theater as tense as any battlefield. In a larger picture, this pivot to aluminum reflected a transformation in American warfare. The United States was beginning to recognize that victory would require innovation as much as manpower. It was no longer enough to rely on traditional materials, established tactics, or slow industrial processes. Speed, adaptability, and creativity would define the nation's ability to project power across oceans and survive in a war unlike any the world had seen. The first aluminum plates were still experimental, their effectiveness uncertain. But the foundations were laid. From the mills to the shipyards, America was learning to do more with less, to substitute ingenuity for scarcity, and to turn a potential weakness into a strategic advantage. The Navy's next challenge was how to scale these experiments, how to integrate aluminum into ships without compromising combat readiness. The story of that effort would define the coming year. By the spring of 1941, experimental aluminum armor had moved beyond theory. The Navy issued preliminary orders for retrofitting select battleships and cruisers, focusing on critical areas: ammunition magazines, engine rooms, and command centers. These were the ship's most vulnerable points, where a single penetrating shell could ignite catastrophic explosions. Every inch of protection mattered. Alcoa's engineers faced a steep learning curve. Aluminum behaved differently from steel under stress. It could absorb energy efficiently, but tended to deform rather than shatter. Welds required precise temperature control, and alloys had to balance hardness with ductility. Standard shipyard procedures were insufficient. New techniques had to be developed while ships continued construction. Time was a luxury they did not have. Across multiple East Coast yards, Boston Navy Yard, Norfolk Naval Shipyard, and Brooklyn's New York Naval Shipyard, teams collaborated in unprecedented ways. Metallurgists, naval architects, and shipbuilders shared experiments, live-fire tests, and performance reports. Plates were layered, bolted, welded, and repeatedly tested against armor-piercing rounds. Engineers recorded deflection patterns, spall formation, and heat resistance, meticulously documenting each result. Failure was common. Some plates buckled under impact. Others warped in the ship's heat, creating gaps. Yet each failure brought new insight, gradually refining designs toward effectiveness. Meanwhile, production had a scale. Aluminum had been abundant in small quantities for aircraft, but the Navy demanded tons of it for massive warships. Alcoa expanded smelting operations, converting civilian production lines into military-grade fabrication plants. Rolling mills ran around the clock, furnaces glowed day and night, and workers faced exhausting shifts to meet the Navy's aggressive timeline. By mid-1941, Alcoa was producing plates thicker and larger than ever before, some reaching several inches in width, tailored to each ship class. The industrial feat was staggering, a testament to both human labor and organizational coordination. Political and strategic pressures shaped these efforts. The U.S. had not yet entered the war, but military planners anticipated confrontation with Japan. Reports from naval intelligence highlighted the vulnerability of U.S. battleships to torpedo attacks and artillery fire, particularly in the Pacific shallow anchorages and confined bays. Aluminum armor was an experimental hedge against these threats, a way to maintain fleet readiness despite steel shortages. Congressional oversight committees monitored costs and timelines, while the Navy balanced secrecy with urgency, ensuring the enemy could not learn of these adaptations. By late 1941, a few ships had received their first aluminum plates. The USS North Carolina, under construction in Norfolk, served as a prototype for integration. Technicians measured, cut, and fitted plates over engine bulkheads, while metallurgists tested impact resistance in adjacent facilities. Each plate represented both an innovation and a gamble. The success of a ship in combat might depend on these sheets of metal. Observers noted the strange juxtaposition. Hulking steel battleships, iconic in size and form, partially armored with a silvery, lightweight metal previously relegated to aircraft wings. These experiments also reshaped naval engineering culture. Officers who had spent decades relying on traditional steel were forced to adapt, trusting the calculations and live tests performed by young engineers. Shipbuilders learned new welding techniques and material handling procedures. The shift was as much intellectual as it was physical. Decades of naval tradition had to bend to meet the realities of wartime resource constraints. The urgency culminated in December 1941, mere days before the attack on Pearl Harbor. Aluminum armor had proven promising in tests, and production lines were operating at full capacity. The Navy faced the looming reality that conflict was unavoidable, and ships equipped with aluminum plates might face their first real trials in the Pacific. Every decision, every innovation carried the weight of national survival. What began as a theoretical experiment in a factory had evolved into a full-scale industrial and military initiative. Aluminum was no longer a supplement. It was a critical element in America's strategy to maintain a viable fleet despite shortages and looming threats. The next question would be how this material, these innovations, would intersect with human lives, leadership decisions, and the tactical challenges of war. In the shipyards of Boston, Norfolk, and Brooklyn, the human dimension of this innovation was palpable. Workers moved like ghosts across icy decks, their faces streaked with soot and sweat. Aluminum plates, lighter than steel yet bulky, required teams of men to lift, align, and weld into place. Every movement had to be precise. One misaligned plate could compromise the ship's balance or leave a vulnerable gap. Hammers, torches, and welding equipment rang out in a relentless rhythm, a chorus of effort against the ticking clock of war. Fatigue and cold were constant adversaries. Winter drafts swept across open decks, and molten aluminum glowed white-hot in the furnaces, a dangerous beacon that demanded unwavering focus. Engineers and machinists worked in tandem with laborers, translating calculations into tangible results. Mistakes could be deadly. In one early test, a poorly bolted plate bent under its own weight, delaying an entire retrofit by days. Yet, amid the strain, camaraderie grew. Men shared tools, knowledge, and encouragement, bound by the knowledge that their labor could save lives thousands of miles away in the Pacific. Aluminum, previously celebrated for its use in aircraft, now faced the unforgiving demands of naval warfare. Engineers had to grapple with its unique properties. Unlike steel, aluminum absorbed impact by deforming rather than fracturing, a behavior that required recalibrating expectations of protective effectiveness. Alloys were adjusted meticulously. Small changes in copper, zinc, or magnesium content could dramatically alter performance. Welding posed its own challenge. Aluminum's lower melting point meant that excessive heat could weaken joints, while insufficient heat risked incomplete bonding. Rolling mills, originally designed for thin sheets, were retooled to produce plates several inches thick, a technological feat previously unattempted at scale. Ballistic testing became a science of its own. Shell after shell was fired at prototype plates, measurements taken with calipers, high-speed cameras, and meticulous logs. Each test informed the next, gradually refining a material once considered unsuitable for armor into a viable alternative for America's fleet. The Navy's leadership faced a paradox of risk and necessity. Admirals and procurement officers had to make decisions under uncertainty, weighing incomplete data against impending threats. Rear Admiral Harold Stark, then Chief of Naval Operations, pushed for accelerated testing despite the unknowns, aware that inaction could leave the fleet exposed. Memoranda circulated up the chain of command. Time is of the essence. The enemy's capabilities are growing daily. Alternative armor solutions must be expedited. At Alcoa, executives balanced national duty with industrial capacity. CEO E.G. Layton coordinated production expansions while maintaining quality control. Managers orchestrated shifts of thousands of workers, navigating union negotiations, labor laws, and logistical bottlenecks. Their decisions were not abstract. Each aluminum plate represented both a technical challenge and a tangible safeguard for sailors' lives. Leadership at every level required a blend of foresight, trust in engineering data, and the courage to embrace unconventional solutions. By the spring of 1941, these three angles, human effort, technological innovation, and decisive leadership, had converged into a high-stakes industrial experiment. Men and machines worked in concert, testing the limits of materials and human endurance. The aluminum plates, glowing under arc welders' sparks, symbolized more than protection. They embodied adaptation, risk, and ingenuity under extreme pressure. Yet the story of aluminum armor did not exist in isolation. It would soon intersect with tactical realities at sea, the perception of America's enemies, and the broader moral and industrial challenges of wartime production. The introduction of aluminum armor forced a reevaluation of naval tactics. Lighter than steel, aluminum allowed ships to retain speed and maneuverability even when critical areas were reinforced. Commanders could plan operations with slightly more latitude, confident that vital sections had a protective buffer. However, aluminum could not replicate the mass and hardness of traditional steel. Naval tacticians had to adjust firing angles, engagement ranges, and ship formations to account for differences in armor resilience. Simulations in the shipyards and test ranges highlighted a paradox. Aluminum reduced overall weight, improving propulsion efficiency, yet could deform under sustained bombardment. Fleet commanders were instructed to protect ships' flanks more aggressively, keeping vulnerable areas out of direct fire while relying on the lighter armor to withstand occasional strikes. The technology did not replace strategy, it demanded its evolution. Every maneuver, every formation was now informed by the capabilities and limitations of an experimental metal. From Tokyo to Shanghai, Japanese intelligence monitored U.S. naval developments with keen interest. Analysts noted the American fleet's increasing reliance on lightweight alloys in aircraft and naval construction, but aluminum armor was a largely unknown factor. To the Japanese, reports of experimental materials suggested innovation, but also potential vulnerability. Would these ships withstand artillery fire? Could aluminum deter torpedoes? The uncertainty worked both ways. The Japanese Navy could not precisely gauge the resilience of retrofitted ships, forcing their strategists to plan with caution. Ironically, the secrecy surrounding aluminum armor amplified its tactical value. The U.S. Navy gained a psychological edge. Even without knowing full effectiveness, the very presence of a new defensive material forced the enemy to hesitate, adding a subtle yet real layer of deterrence before any shots were fired. The rapid industrialization required to produce aluminum armor carried profound moral implications. Workers labored under grueling conditions, often facing exhaustion, injury, and extreme weather. Factories ran 24-hour shifts, with the glow of furnaces illuminating tired faces and foreboding shadows. Managers balanced production quotas against human safety, making decisions that could directly affect lives. Each plate represented both protection for sailors and a risk for the man who forged it. At a broader level, aluminum armor illustrated the ethical dimension of wartime industrial innovation. The U.S. had opted to substitute a non-traditional material for steel, knowing that untested solutions could fail under fire. Engineers and leaders wrestled with the tension between necessity and risk, between speed and reliability. Yet, in these constraints, a moral clarity emerged. The goal was survival, not perfection. The workforce, the engineers, and the Navy accepted the hazards of experimentation because the stakes, human lives and national security, demanded it. By mid-1941, these angles, tactical adaptation, enemy perception, and moral industrial responsibility converged into a singular reality. Aluminum armor was no longer a theoretical solution. It had become a defining element in America's preparation for war. Battleships were partially armored with this lightweight alloy. Officers adjusted their tactics accordingly, and the workforce endured conditions that few civilians could imagine. By mid-1941, the first aluminum plates were ready for rigorous testing. At the Norfolk Naval Shipyard, engineers assembled a live-fire range designed to replicate the extreme conditions of naval combat. Target hulls, reinforced with aluminum alloys of varying thicknesses, were positioned at precise distances. Naval officers, metallurgists, and shipbuilders watched from protective positions, the tension palpable. The stakes were unmistakable. These trials would determine whether a lightweight metal could actually save lives in battle. The first series of tests began with medium-caliber artillery, 5-inch shells, standard for destroyer engagements. Aluminum plates absorbed the initial impacts with minimal penetration, deforming under the force but holding structural integrity. Observers noted the spall patterns carefully. Small fragments broke free from the plate's interior, a danger mitigated by additional backing layers. Engineers recorded every measurement, every crack, every dent. The data was meticulously logged, forming the basis for naval deployment decisions. Next came the heavier guns, 14-inch and 16-inch shells, capable of crippling a battleship. The tension was almost tangible as each round was fired. Some plates buckled under impact, bending outward dramatically, but crucially, none failed catastrophically. Aluminum's capacity to absorb kinetic energy by deforming rather than shattering proved promising. Officers whispered to one another. If these results held in real combat, the fleet's most vulnerable compartments could survive strikes previously assumed fatal. Meanwhile, at Alcoa's plants in Pennsylvania, production lines churned in synchronization with testing. Adjustments were made in real time. Alloys were tweaked, thicknesses recalculated, and welding methods refined. It was an industrial ballet of precision and urgency. Every plate produced carried the weight of the data streaming in from Norfolk, shaping each subsequent iteration. Engineers worked feverishly, knowing that any delay could leave the fleet exposed. By autumn 1941, experimental aluminum armor had been installed on select vessels. The USS North Carolina, partially armored over engine rooms and magazines, became a prototype for operational evaluation. Technicians meticulously bolted and welded each plate, ensuring alignment with structural reinforcements. The ship's officers ran repeated drills, evaluating stability, speed, and maneuverability. Aluminum, far lighter than steel, allowed the ship to maintain maximum speed, a crucial advantage in potential Pacific engagements. Tests extended beyond artillery. Simulated torpedo blasts examined how aluminum plating could mitigate explosive force. While not impervious, aluminum layers absorbed shock and reduced hull breach size, limiting flooding. Engineers noted that layered application, rather than a single thick sheet, provided optimal performance, a revelation that would shape fleet-wide deployment. These insights proved the material's viability under multifaceted threats, bridging the gap between laboratory testing and real-world application. Leadership decisions intensified as the attack on Pearl Harbor loomed on the horizon. Admirals and Navy engineers debated where aluminum armor should be prioritized. Critical areas, such as magazines and engine rooms, took precedence, but officers also advocated for experimental installation along secondary belts and deck surfaces. Each decision involved a balance between protection, weight, and ship stability, a calculus where misjudgment could prove fatal in the first hours of combat. Simultaneously, intelligence reports warned that Japan's fleet was increasingly aggressive in the Pacific, and air reconnaissance suggested new classes of enemy warships capable of delivering devastating firepower. The clock was ticking. America's fleet, though still officially unengaged in war, faced a rapidly evolving threat environment. Aluminum armor had to perform flawlessly the first time, or the consequences could be catastrophic. In December 1941, just days before Pearl Harbor, aluminum armor reached operational readiness on multiple vessels. The Navy now possessed a fleet partially protected by an innovative material born out of necessity. Tests had demonstrated both promise and limitations, but officers and engineers shared a cautious optimism. Aluminum had survived artillery, torpedoes, and structural stress in controlled conditions. And now the true test was imminent: battle. The convergence of human effort, technological ingenuity, and leadership decisiveness had brought the experimental material from factory floor to fully outfitted warship. Yet despite this achievement, uncertainty remained. How would aluminum armor fare against a live enemy attack? Could it save the lives of sailors under fire? The answers were about to be written in steel, fire, and smoke across the Pacific. December 7th, 1941, Pearl Harbor. While aluminum-plated ships were still a minority in the fleet, their presence marked a new chapter in American naval defense. USS North Carolina, though not yet in Hawaii, represented the promise of innovation, a blueprint for survival in a war that had just erupted. Across the Pacific, ships retrofitted with experimental aluminum armor began their initial deployments, their crews unaware that a single sheet of metal might determine the fate of hundreds of lives. In the weeks following Pearl Harbor, patrols and convoy escort missions became the first operational tests of aluminum armor. Reports trickled back to Norfolk and Washington. One cruiser, retrofitted with layered aluminum plates over its engine compartments, survived a torpedo near-miss with only minor flooding. Observers noted that the aluminum plating had absorbed a portion of the explosive force, preventing catastrophic damage. For engineers and officers monitoring the fleet, these early reports were electrifying. The theoretical experiments of the past year had produced tangible results. Aluminum armor also influenced tactical behavior in real time. Commanders adjusted formation patterns to maximize the protective advantage while minimizing exposure. Ships with lighter aluminum plating could maneuver more quickly, evading enemy fire and positioning themselves for counterattacks. Fleet exercises demonstrated that speed and adaptability, when combined with targeted armor, could compensate for numerical or firepower disadvantages. Aluminum had not transformed ships into invulnerable fortresses, but provided an edge, a measure of resilience that steel shortages had denied. The Japanese Navy, unaware of these deployments, continued aggressive operations, expecting U.S. ships to be vulnerable to conventional artillery. The unpredictability of aluminum's performance added a subtle layer of deterrence. Commanders reported encounters with enemy forces where their ships withstood bombardment better than anticipated, buying time to regroup or retreat. Each successful defense reinforced confidence in aluminum's role as a critical wartime innovation. Back at the factories, production accelerated. Lessons from operational use fed directly into Alcoa's lines. Alloy compositions were refined based on reports from the Pacific. Welding techniques were adjusted to reduce structural stress under repeated fire. Engineers developed layered configurations, using multiple thin sheets to absorb shock more efficiently than a single thick plate. The collaboration between frontline data and industrial capacity created a feedback loop that allowed rapid improvement, a synergy rarely seen in traditional naval development. The human element remained central. Sailors aboard these ships often marveled at the new armor, noting the differences in weight and handling compared to traditional steel. Maintenance crews learned to inspect aluminum plating for deformation rather than cracks, adapting their routines to the metal's unique properties. Engineers and officers communicated closely, ensuring that every modification enhanced survivability without compromising stability or speed. By mid-1942, several battleships and cruisers had received full retrofits of aluminum armor over critical areas. In early engagements across the Pacific, including convoy protection runs and skirmishes near the Solomon Islands, aluminum-equipped ships demonstrated increased resilience. They survived near-direct hits and shrapnel strikes that might have crippled older, steel-only vessels. Reports highlighted reduced casualties in protected compartments, validating the material's strategic value. The climax of this innovation was not a single battle, but a convergence of experimentation, industrial might, and combat necessity. Aluminum armor had moved from laboratory testing to factory production to operational deployment within a year, an unprecedented pace for naval engineering. It transformed American warship design under pressure, compensating for steel shortages and providing the Navy with a lifeline during its most vulnerable period. The fleet now faced a harsh reality. The war was escalating, and aluminum armor would be tested repeatedly. Every deployment, every engagement would measure the success of a year's worth of ingenuity. The outcome of future battles and the lives of sailors aboard these ships depended on how well this unorthodox material could perform under fire. And yet, even as victories and near misses accumulated, the story was only partially written. The aftermath of aluminum armor's introduction would reveal not only its tactical and technological impact, but also the broader implications for industrial innovation, naval strategy, and the human cost of war. By mid-1942, the first wave of aluminum-armored ships had proven their worth. Operational reports confirmed what engineers had hoped. Critical areas reinforced with aluminum had survived strikes that would have devastated unprotected steel hulls. In one Pacific convoy engagement, a cruiser outfitted with layered aluminum plates over its engine room sustained a near-direct hit from a Japanese 14-inch shell. The plate deformed outward, absorbing a substantial portion of the impact, preventing catastrophic flooding, and allowing the ship to maintain speed and continue escorting vital transports. The crew's survival and the ship's continued operational capacity marked a turning point in the Navy's confidence in alternative armor solutions. Damage reports emphasized that aluminum's lightness was a key tactical advantage. Ships retained speed and maneuverability, enabling evasive maneuvers and rapid repositioning during engagements. Commanders documented improved survivability without sacrificing mobility, a balance previously impossible with steel alone. This allowed fleet planners to deploy ships more aggressively, particularly in escort missions and high-risk patrols, where traditional battleships might have been forced to remain in reserve. Industrial lessons were equally profound. Alcoa's success in scaling aluminum production to meet naval demands showcased the United States' capacity for rapid wartime adaptation. Smelters operated at unprecedented throughput. Rolling mills expanded to handle thick plates, and engineers optimized alloy compositions based on operational feedback. Coordination between factories and shipyards became a template for subsequent wartime industrial programs. What began as an experimental innovation evolved into a reliable, reproducible process, a model of industrial ingenuity under pressure. The human toll and workforce transformation were also stark. Shipyard workers endured long shifts in extreme conditions, balancing speed with precision. Engineers adapted their designs on the fly, integrating feedback from live-fire tests and operational deployments. Labor strikes, previously a potential bottleneck, were mitigated through careful negotiation and the shared sense of national purpose. The workforce itself became a critical component of America's ability to deliver functional aluminum armor on time. Yet limitations persisted. Aluminum was not a universal solution. Heavy shell fire could still compromise the armor if concentrated on unreinforced areas. Torpedo attacks remained deadly, and the plates required careful installation to avoid structural weaknesses. The Navy quickly learned that aluminum armor was a supplement, not a replacement for traditional steel, a lesson reinforced in after-action reports. Officers emphasized that the metal's effectiveness depended on strategic placement and proper integration with ship design rather than blind reliance on its novelty. Strategically, aluminum armor shifted naval planning. Ships could now engage in riskier operations, cover longer distances, and protect vital supply convoys without relying solely on escort vessels for defense. Fleet exercises demonstrated that ships retrofitted with aluminum maintained higher operational readiness during sustained deployments. Reports highlighted fewer critical failures under attack and a measurable reduction in crew casualties in protected compartments. Historians would later describe this period as a turning point in U.S. naval resilience during the early months of the Pacific War. As 1942 progressed, the Navy committed to a broader deployment of aluminum armor. New constructions incorporated the lessons learned from early retrofits. Aluminum plating became standard for critical areas in cruisers, destroyers, and battleships where steel shortages persisted. The innovation demonstrated that wartime ingenuity, guided by necessity, expertise, and industrial capacity, could compensate for material scarcity and shape the outcome of engagements far from American shores. By combining human effort, industrial innovation, and strategic foresight, the United States had turned a potential vulnerability into a tactical advantage. The first phase of aluminum armor had ended, but the next chapter would reveal its long-term impact on ship design, fleet strategy, and the broader trajectory of naval warfare. By late 1942, aluminum armor had transitioned from experimental innovation to a cornerstone of American naval strategy. Lessons from early deployments informed the retrofitting of multiple cruisers, destroyers, and battleships. Critical compartments, magazines, engine rooms, and command centers were consistently reinforced, creating a new baseline for survivability in the fleet. The Navy recognized that aluminum could never replace steel entirely, but had become an indispensable supplement, allowing ships to endure damage that would have previously been catastrophic. Operational records from the Solomon Islands and Coral Sea campaigns highlighted aluminum armor's tangible benefits. Several cruisers, subjected to concentrated Japanese shell fire, sustained damage without catastrophic flooding. While steel might have absorbed more force, aluminum's lighter weight preserved speed and agility, enabling evasive maneuvers that likely saved additional lives. Commanders reported that even minor hits caused less structural compromise than anticipated, providing both physical protection and a psychological boost for crews confronting an increasingly lethal enemy. Industrial lessons were equally transformative. Alcoa and its partners refined smelting, rolling, and tempering processes to produce armor plates at an unprecedented scale. Production lines incorporated feedback from operational theaters, adjusting alloy compositions and plate thicknesses to maximize resilience. Coordination between the Navy and private industry became a model of wartime efficiency, demonstrating that rapid adaptation, precise engineering, and flexible logistics could overcome material shortages. Aluminum armor became a proof of concept for the broader wartime industrial mobilization that would characterize the U.S. war effort. Engineers and naval officers reflected on the broader implications. In letters and reports archived in naval records, Metallurgists noted how aluminum's unique deformation under fire required new inspection routines and maintenance protocols. Officers documented changes in tactics, emphasizing that speed, maneuverability, and layered armor could offset vulnerabilities. The lessons learned from aluminum would influence ship design for decades, shaping post-war considerations in naval architecture and armored protection. The human dimension remained central. Factory workers, shipbuilders, and engineers who had labored under grueling conditions saw the fruits of their efforts in real-world deployments. Each aluminum plate represented a tangible contribution to survival, a reinforcement of critical compartments, a shield against fire, and, above all, a lifeline for sailors on the front lines. This shared purpose forged a sense of unity across industrial and military spheres, illustrating how coordinated effort could translate into strategic advantage. The legacy of aluminum armor extended beyond immediate tactical gains. By demonstrating that unconventional materials could meet operational needs, the program encouraged further innovation in military engineering. Lightweight alloys were integrated into new ship designs, aircraft, and even experimental vehicles. The initiative also reinforced a core principle of wartime production. Necessity drives innovation, and industrial flexibility can turn scarcity into strength. Yet the program also revealed limitations and costs. Aluminum's effectiveness was situational, dependent on placement, layering, and integration with other ship systems. Not every strike could be absorbed, and the metal required ongoing maintenance to remain effective under prolonged deployment. Nevertheless, the early successes provided a foundation for confidence. Naval planners understood that even partial protection could have a decisive impact in engagements where a single hit could mean the difference between survival and loss. By the end of 1942, the United States had effectively transformed a potential vulnerability into an operational advantage. Aluminum armor had protected key ships, informed fleet tactics, and proven the nation's industrial ingenuity under pressure. The combination of human effort, technological innovation, and strategic foresight had established a template for wartime problem-solving. From the icy docks of Boston to the battle-scarred waters of the Pacific, the metal that had once seemed unsuited for naval warfare had become a critical component of America's fight for survival. The stage was now set for reflection. The broader significance of aluminum armor for industry, naval strategy, and human ingenuity would resonate long after the immediate battles had ended. Aluminum armor was born of necessity, yet it became a testament to American ingenuity. In 1941, the Navy faced a stark reality. Steel, the material that had long defined battleship strength, was in critically short supply. Traditional solutions were too slow, too heavy, too constrained by global shortages. In that moment of scarcity, innovation became survival, and aluminum, once relegated to aircraft wings and consumer goods, emerged as a lifeline for America's fleet. The story of aluminum armor is more than a tale of metallurgy. It is a story of human determination under pressure. Shipyard workers braved freezing decks and molten furnaces. Engineers translated theory into life-saving practice, and leaders made high-stakes decisions with incomplete data. Every plate forged and every weld completed represented not just metal, but the lives of sailors who would one day trust these ships in battle. The material itself became a symbol of collaboration between labor and leadership, between industry and military, between necessity and invention. Strategically, aluminum armor reshaped naval operations. It allowed speed and maneuverability to coexist with protection, demonstrating that adaptability could compensate for scarcity. Early engagements in the Pacific proved that even a partial solution could save lives and influence outcomes. The lessons extended beyond World War II. American industry learned that unconventional approaches, when combined with precise engineering and decisive leadership, could overcome material limitations and redefine what was possible in warfare. But there is a deeper resonance. Aluminum armor reminds us that innovation often emerges from constraints, and that human ingenuity is as much a weapon as any gun or shell. The success of these ships depended on minds, hands, and courage as much as on metal. In a world descending into chaos, America's response was not simply to wait for resources to arrive, but to invent, adapt, and persevere. In the end, aluminum armor was not just protection. It was a statement that adversity could drive ingenuity, that scarcity could inspire invention, and that human effort, when coordinated with vision and purpose, could bend the course of history. From the icy docks of Boston to the battle-scarred waters of the Pacific, a lightweight metal carried the weight of survival and left a lasting imprint on naval warfare, industrial strategy, and the story of a nation rising to meet the demands of total war.